All right, so in this case, we're going to look at an example where we use tabulated free energies of formation to calculate delta G naught for a reaction. And here's the reaction that we want. Now we do have to be careful. The free energies depend strongly on temperature. So we have to make sure that the temperature that they want is the same as the temperature that our values are tabulated for. In this case, that's true. So we're good. We can just use the free energies of formation, right? And what we want to do, sort of in its simplest form, delta G naught reaction is the free energies of formation of the products minus the reactants. So I'm just going to add up the free energies of formation of the products, subtract from that the free energies of formation of the reactants, being sure to take into account the stoichiometric coefficients. So if I wanted to calculate delta G naught for this reaction, so I start with the products. So I have 2 moles of iron. Now, if you notice, I purposely left that blank. And that's because I wanted to emphasize and remind you that the free energy of formation of any element in its standard state, and the standard state of elemental iron is a solid, the free energy formation of an element in its standard state is always going to be 0. And the same thing is true for the enthalpies of formation. So I'll go ahead and put those in. But you want to remember this because on a test or a quiz, when I give you one of these tables, I probably will leave these entries blank because I want you to remember that the free energy of formation and the enthalpy of formation of an element in its standard state is 0. All right, so now back to this problem. So I have 2 times 0 for the iron, and I have 3 moles of CO2 gas. I also wanted to emphasize how important the phases are. So notice I've included CO2 gas and CO2 aqueous in this table. Right? We have gaseous CO2, not aqueous, so I want to be sure that I use the correct values. You notice that in the different phases or the different states, the values are not the same. So we want to be sure that we're aware of that. All right, so I've got 3 moles of CO2 gas. So that'll be 3 times negative 394.4. And now I need to add up the reactants and subtract that from the products. So it's important to be careful with your signs. So what I usually do is I do minus. So I've got the products here, and then I put all the reactants inside these brackets. And so I have 1 mole of Fe2O3, so that'll be negative 742.2. And then I have 3 moles of carbon monoxide, so that's negative 137.2. All right, so now if we do a little bit of arithmetic, 3 times negative 394.4, I get negative 1183.2. And then it's minus, and I'll add up everything inside the brackets. And so when I do negative 7042.2 plus 3 times negative 137.2, I get negative 1153.8. All right, and so now I have negative 1183.2, and then minus a negative is a positive, so then I have plus 1153.8, and that gives me a final value of 29.4. And then all of these values were in kilojoules per mole, so then when I add and subtract, I'll get the same units. So my units will be kilojoules per mole. All right, next we'll look at another example. All right, so now we want to calculate the free energy change of the reaction, but at 525 Kelvin. And because delta G depends so strongly on temperature, I can't use the values tabulated for 298. But one assumption that we often make is that enthalpy, delta H, and entropy, delta S, do not depend on temperature. So what I can do in this case is I can use these tabulated values to calculate delta H and delta S, and then I can use the fact that I know that delta G is equal to delta H minus T delta S. So I can calculate delta H and delta S from the table, and then use this equation to get delta G. All right, so I'm going to break it up on a couple slides so I don't cram in too much. So the first thing I want to do is calculate delta H for this reaction. And this works just like we did previously for delta G. So it's going to be the products minus the reactants. And again, the free energy of formation of an element in its standard state is 0. So the delta H for this reaction is going to be 2 times 0 3 carbon dioxides, so that's negative 393.5. And then that's the products, so then minus the reactants. And again, I put all the reactants in brackets. And so for the Fe2O3, I have negative 824.2, and then plus 3 times the carbon monoxide, negative 110.5. And so then 3 times negative 393.5, I'm getting negative 1180.5. And then minus, when I add all that up inside the bracket, I'm getting negative 1157.7. And then again, negative 1180.5 minus a negative is a positive, so I have plus 1157.7. And that gives me a delta H for this reaction of negative 24.8. And again, the units on delta H, just like on delta G, are going to be in kilojoules per mole. All right, so let me go to the next slide and we'll do the same thing for the entropies. All right, and now calculating delta S for a reaction works just like delta G and delta H did. So I have 2 moles of iron. And then minus, again, I'll put all the reactants in brackets. My Fe2O3 is 87.4 plus 3 times 197.7. All right, and now I'm getting, when I add up all of these guys, I get 696, and then minus inside the brackets, I get 680.5. And for delta S naught reaction, I'm getting 15.5, but now the units are joules per mole dot Kelvin. All right, and we'll finish this up on the next slide. All right, so I've collected the information from our previous work here. So now that we know delta H and delta S, I can plug that into this equation. Delta G is equal to delta H minus T delta S. But I have to be careful with my units. The delta H is in kilojoules per mole, and delta S is joules per mole dot Kelvin. Now the Kelvin will be taken care of. When I multiply that by the T, the Kelvins will cancel, but I can't add joules to kilojoules. So this is joules per mole dot Kelvin. What I want to do is convert this into kilojoules per mole dot Kelvin. So if I do that, 15.5 joules over moles dot Kelvin, and then times, we know that there are 1,000 joules in 1 kilojoule. So my delta S is 0.0155 kilojoules per mole dot Kelvin. All right, so now I can plug everything in. So delta G is going to be delta H, so that's negative 29.4, and then minus, oh, not 500, 525. Times 0.0155, right? And let me write the units down underneath, right? So this is kilojoules per mole. The temperature is in Kelvin, and I'm multiplying that by kilojoules per mole dot Kelvin. So the Kelvins cancel, and so now it's, when I add things, they have to have the same units, and they're both in kilojoules per mole, so that is good. So then I get, when I plug this in my calculator, for delta G, I get negative 37.5 kilojoules per mole.